All right, gentlemen, we're going to take a look at the second part of Chapter 3. And we moved from kind of an overview, introduction to everything, to some specifics about the geosphere. And now in this section, we're going to look at the atmosphere. Here again, these are just all of the main points of interest for this part of the chapter. Once again, your objective questions, understanding these, being able to answer these, put you in a good position, not only for the oral quiz, but for the written test at the end of the week as well. All right, the atmosphere, as we saw, is one of these parts or divisions that the Earth is broken up into, and the atmosphere is a mixture of gases that surrounds the planet. And if you go back and look at those diagrams, you can see where, what the boundaries of the atmosphere are, or how thick it is. It's not just, by the way, something that exists on planet Earth. It's the mixture of gases that surrounds a planet. And so we can talk about different atmospheres for different planets, and different planets are going to have different atmospheres. So as I was saying, different planets have different atmospheres made up of different mixtures of gases. We're going to specifically look at the atmosphere of the Earth. And the three main gases that we talk about are nitrogen, oxygen, and carbon dioxide. Those by no means are the only gases. There are lots of other gases, lots of gases in very small quantities or small percentages, but those are the three main ones. And gases are added to and removed from the atmosphere. This is one way or the other, this is connected to mostly living organisms, but, and especially in terms of the discussion today regarding global warming, it is not only living organisms. There's lots of research out there that shows that the vast majority of carbon dioxide that is pumped into the atmosphere today, it continues to be through volcanic action. So this is something to keep in mind. With that being said, it's a dynamic, in science we can think of this as a dynamic system. The percentages or the amounts basically stay the same in one sense, in the short term. In the long term they are changing, but this is as gases are being added and gases are being removed. Evaporation of the surface of the ocean adds gas, and temperature gradients cause gas to dissolve into the water of the ocean. That's removing gases from the atmosphere. So it's a system that is constantly in flux. But on a basic level, we know that animals remove oxygen when they breathe in, and they add carbon dioxide when they breathe out. Plants do the opposite. Volcanic eruptions, as I said, add gases to the atmosphere. Things that humans do, the equipment that we use, vehicles, add and remove gases. Another important aspect of the atmosphere in a discussion of the intricacies of how all this works is the fact that the atmosphere insulates the Earth's surface. And what we mean by this is that there is a perfect percent composition of the atmosphere that allows for the temperature of the surface of the Earth to be in a range that sustains life. Okay, insulation slows the rate at which the Earth's surface loses heat, and it keeps the Earth's temperature at which living things can survive. And this is a very specific, this is a very narrow window. And that's important to understand, to recognize. A function of the atmosphere on the Earth is connected to the temperature of the surface of the Earth. The composition of the atmosphere, or what is the atmosphere made of? Nitrogen makes up 78% of the Earth's atmosphere. So by and large, the vast majority of gas that is in the Earth's atmosphere is nitrogen. Enters the atmosphere when volcanoes erupt. It enters the atmosphere when dead plants and animals decay. Oxygen is the second most abundant gas in the atmosphere. Oxygen exists in the atmosphere primarily as it is produced by plants. The atmosphere is not just gases, and there are lots of other gases besides the two that we mentioned. The atmosphere has lots of tiny solid particles, atmospheric dust, we can call it. This is our understanding of how clouds are formed between moisture and water and particles. We get cloud formation. In addition to nitrogen and oxygen, lots of other gases, argon, carbon dioxide, methane, water vapor make up the rest of the atmosphere. And you can see how that works out in this pie chart here. We said that nitrogen makes up 78% of the atmosphere. Oxygen is approximately 21%, and that is going to leave us 1%. And all the other gases that we talk about fall into that 1% slice of the pie. That's very important because it gives us a sense, a feeling, an understanding for how small, in terms of percent composition, those other gases are. But I will say this, in terms of importance of gases, certainly the amount of a gas that exists in the atmosphere is not necessarily directly correlated to its importance. Okay, we know that oxygen is very important because that's what animals breathe, but it doesn't make up the most. It's at 21%. It's less than a quarter, and yet it seems to be perfectly proportioned for us to be able to breathe it. On the other hand, in terms of greenhouse gases, we always seem to hear quite a bit about the importance of carbon dioxide or carbon monoxide, the carbon gases that go out and are greenhouse gases, and the increased amount increases the greenhouse effect. And yet, atmospheric scientists will say, and have said and continue to say, that the most important greenhouse gas is water vapor. Okay, both of those on the very small end of the scale of how much is present. Air pressure is another important aspect of the atmosphere and what's going on with the atmosphere. To have a basic understanding of air pressure and how it works, what's going on here, we need to understand that the Earth's atmosphere, or air, okay, is matter, right? So it's made up of stuff, those stuff being particles. Right? Gas is matter. You can have a certain volume of water, and that volume of water can exist as a liquid, it can exist as a solid, it can exist as a gas. But gases are stuff. It is matter. And we have the force of gravity on the planet. Okay? And what the force of gravity does is it, in a sense, pulls the stuff of the atmosphere, the matter, toward the Earth's surface. And through this action, through this mechanism, the atmosphere is denser the closer you get to the Earth's surface. Okay? Almost the entire mass of the Earth's atmospheric gases is located within 30 kilometers of the surface. But when we talk about atmospheric pressure, and we talk about what that is, atmospheric pressure at sea level is different, and it's higher, okay, than pressure, or barometric pressure, we could also use that term, at the top of Mount Everest. And so this is very important because pressure ends up having to do with certain functions, biological functions, like breathing, as well as other things. But we've got to try to grasp and try to understand here that this pressure has to do with the fact that the atmosphere is made out of matter. Matter is pulled toward the Earth due to the force of gravity. And as I said, with my example, the farther away you go from the surface of the earth, or the more elevation you gain, the less dense the air becomes. This is connected to breathing, and breathing being more difficult at mountain elevations. We talk about thin air and things like that. Talk about there being less oxygen. And those are all euphemisms that we use. But the issue has to do with pressure. And let me briefly, I'll try to go over this and demonstrate this in class as well. But the way that your lungs work, okay, when your diaphragm lowers, that the diaphragm lowering is the muscular mechanism for taking a breath in. When your diaphragm lowers, it increases the volume of your thoracic cavity. Your thoracic cavity is where your lungs are found. And when it increases the volume, okay, it kind of creates a bit of a vacuum. And the pressure of the air outside of your lungs is greater than the pressure of the air inside, because that volume has increased, creating a bit of a vacuum. And the air is always going to travel according to the pressure gradient, and that means the air will move from a place of higher pressure to a place of lower pressure. And so what happens is the air rushes into your lungs. And then this pressure also has to do with the exchange of the gases between your membranes, your alveoli, the sacs in your lungs, and your blood. But that's how it gets in. When you exhale, when you breathe out, your diaphragm moves up. And even to a degree, your rib cage squeezes a little bit. And when that happens, it decreases the volume in that space, in that thoracic cavity. And if we, get into chemistry, you talk about the gas laws. If you decrease the volume, you've got an amount of gas, and you decrease the volume, you increase the pressure. So now the pressure inside of your lungs is greater than the pressure in your surrounding environment. And again, the gas is going to want to travel from an area of greater pressure to an area of lower pressure, and the air moves out of your lungs into the environment, okay? As you move up in elevation, they call it mountain climbers sickness and things like that. As you move up in elevation, you have a particular challenge, because the pressure, the atmospheric pressure at a higher elevation is less. And that throws off, it begins to move out of the range, the workable range of the mechanics of your lungs and your diaphragm and all that. And that's why higher elevation or less pressure makes it more difficult to breathe. Okay, it is why when an airplane, which is very, very, very high, and the cabin depressurizes, the oxygen masks fall. Okay, not because there isn't necessarily oxygen at that altitude, but because the pressure is so low at that altitude that your body mechanically can't actually work within the parameters of that very low pressure. So you need to increase the percentage of the oxygen, which is the pure oxygen coming through the oxygen masks, so that you can increase the efficiency of your body being able to actually breathe and take the oxygen into your bloodstream. And that's how all that is connected. We will break up the layers, the atmosphere into layers, much like we broke up the geosphere into layers, and we're going to divide the atmosphere into 4 layers. And these 4 layers are not, I want you guys to note this, and we're going to go over this section in class as well, because this is a very tricky section. But these 4 layers are not based on height or altitude. Okay? These 4 layers, the boundaries of these layers are based on temperature changes. But these temperature changes occur at specific altitude marks, and therefore we are able to mark off the altitude where one layer stops and another layer begins. But it's not because we just arbitrarily stated, well, that's going to happen at this altitude. It's because that's where we saw the temperature change take place. Okay? These are the troposphere, the stratosphere, the mesosphere, and the thermosphere. I want you guys to recognize something. We saw mesosphere already. So we've got one term that defines a structural layer in the geosphere mesosphere, and we've got the same term that describes or explains a layer within the atmosphere. So you have to understand context. Do not get them mixed up. You have to understand whether you're talking about the atmosphere or whether you're talking about the geosphere when the mesosphere comes up. This diagram, which I'll show again in class and go over, basically shows these different layers, and it shows that they are a function of temperature, and that temperature ends up displaying itself in terms of altitude. Okay, let me just point out a couple of things on this briefly, and then I'll go over it again in more detail in class. Your bottom x-axis, okay, that shows temperature, and temperature increases from left to right on the bottom x-axis. Notice it starts at negative 80 degrees Celsius. Over at the other end, you have 0, you have 10 degrees Celsius, you have 20 degrees Celsius. Your y-axis lays out for us altitude in kilometers, and the altitude increases from the bottom to the top. So notice where the y and the x meet, you have 0 again, and then it goes from 10 to 20 to 30, all the way up to the upper end, which it would be 600 kilometers. And then the top axis is also showing pressure. I don't go into too much detail in terms of pressure. The green line represents the pressure and shows what happens to the pressure as altitude increases and as temperature. The red line is going to show the temperature. And so I want to use the red line as an example. Notice within the troposphere, this is the first layer, okay, the closer you are to the Earth, all the way over to between the 0 and the 10, 0 and 10 degrees Celsius, the closer you are to the Earth within the troposphere, the warmer the temperature is. As you rise in altitude, you read that red line backwards. As you rise in altitude, okay, the temperature decreases. Notice the red line is starting near the 0 mark, between 0 and 10 degrees Celsius. As I go higher, it backtracks and the temperature is decreasing. So near the top end of the troposphere, which would be, looks like it's right around 15 kilometers in altitude, the temperature within the troposphere is its coldest between negative 50 and negative 60 degrees Celsius. So that works backwards. But when we enter into the stratosphere, which is the next layer, as you go up, watch what happens to that red line. As I go up in altitude, the red line curves back to the right. And so we actually see an increase in temperature. And this is the challenge with the atmosphere. We tend to intuitively think that the higher we go, the colder it gets. And that is true in some of the layers, but it is not true in all the layers. In the troposphere, the higher you go, the colder it gets. But once you enter into the stratosphere, the higher you go, the warmer it gets. And notice at the top end of the stratosphere is the ozone layer. And we'll talk about what that is. As I enter in at right about 48 kilometers, as I move into the mesosphere, notice what happens again. As I gain more altitude, the temperature decreases. Until finally, at about 80 kilometers, I enter into the thermosphere, which is the last layer of the atmosphere. And as I gain altitude, again, we see the temperature increasing. And we'll go over this in more detail in class, so I can put it up on the board and talk about it. But let's talk about each of those layers. The troposphere, lowest of the atmosphere, closest to the Earth, as you saw in that diagram. In terms of temperature, and this layer temperature drops at a constant rate as the altitude increases. We saw that in the graph, right? As you go higher in the troposphere, the temperature goes lower. The troposphere is where weather conditions exist. The weather that happens, that we experience on the surface of the Earth, happens within the troposphere. It is the densest it's the densest atmospheric layer, and that should make sense because I've already explained that the closer you get to the Earth, the more dense the atmosphere is, and the troposphere is the layer that is closest to the Earth. Okay, extends to 18 kilometers above the Earth's surface. And we move up into the stratosphere. It's immediately above the troposphere, and we find it between 18 and 50 kilometers above the Earth's surface. Again, with this layer, it's not a function of that altitude. That altitude is just where those temperature changes exist. What's interesting about the stratosphere is temperature rises as altitude increases. But why does this happen? It is correct to intuitively think the higher you go, the colder it's going to get because of what we experience, what we maybe know about outer space. But then it doesn't play out that way. Why is that? This is why. Because within the stratosphere, there is the ozone and the ozone layer. And the ozone actually has the ability to absorb UV energy from the sun. And because the ozone is there and only in the stratosphere, and the ozone has this unique ability to absorb that UV energy, it actually warms the air within the stratosphere. And because the ozone layer is closer to the top part of the stratosphere, it warms that air within the stratosphere first. So as you move through the stratosphere from lower to higher altitudes, you actually move from lower temperature to higher temperature. Talking about the ozone is a natural existing gas. It's 3 oxygen molecules bonded together. So in terms of chemistry, oxygen is what we generally consider it a diatomic molecule. When we write oxygen, we always write it as O2 because that's generally how we find it in nature, 2 oxygens bonded together. But there is 3 oxygens bonded together, and that's called ozone. Just about all the ozone in the atmosphere is concentrated in the stratosphere. So that's why we say oxygen is a diatomic molecule, because we tend to find it here close to the Earth as 2 oxygen atoms bonded together. All the ozone is in the stratosphere. Ozone has this unique property of being able to absorb ultraviolet radiation. That's important to our understanding of how the planet works, in that it actually reduces the amount of UV radiation that reaches the Earth. And this is important because we know that UV radiation can damage living cells. We know that it causes mutations in the DNA. It is why we use UV radiation to disinfect, to kill bacteria. We have UV radiation lamps that well water runs through in a disinfection process. You'll be in restaurants and see on the wall in those kitchens those little boxes with the UV lights, the purple lights. It's all connected to this idea that we know that UV radiation damages living cells by messing with the DNA. As we continue to move, we move up into the mesosphere. This is the layer above the stratosphere. It extends up to about 80 kilometers. It is the coldest layer of the atmosphere. So, we said there's 4 layers as you move from the surface of the Earth up. We've mentioned 3. The mesosphere is the 3rd one. And yet, even though there is one above the mesosphere is the coldest. Temperatures have been measured as low as negative 93 degrees Celsius within the mesosphere. And this brings us to the thermosphere. This is the layer of the atmosphere located farthest from the Earth's surface. It is where nitrogen and oxygen are present, and they absorb the solar radiation because they are closest to receiving that solar radiation unhindered. And because of that, even though it's the farthest layer of the atmosphere away from the Earth's surface, we know that temperatures can be measured and can reach 2,000 degrees Celsius. Now, what's a bit challenging for us to wrap our minds around is that by the time you get to the thermosphere, the air is pretty thin. There are not a lot of oxygen and nitrogen particles around. And because there are so few nitrogen and oxygen particles, they rarely collide. Even though there's a tremendous amount of energy, there's very little heat transfer because the particles are not colliding one into another, and therefore it would not environmentally feel hot to us. So what this means, guys, is that we have to understand temperature is really a measurement of energy. When that energy is transferred, we feel it as heat. But you can have increased energy to 2,000 degrees Celsius. You can have increased energy without the ability for the transfer of that energy or the heat because there's so few particles, and therefore it doesn't come off to us as being hot. But in terms of straight temperature, the thermosphere being the upper level of the atmosphere, having solar radiation reach the particles of oxygen and nitrogen unhindered, it is the warmest layer of the atmosphere with temperatures reaching 2,000 degrees Celsius. What's very interesting, a phenomenon that's connected to this, is that you have nitrogen and oxygen atoms that receive this energy, X-rays and gamma rays, unhindered, and the atoms become electrically charged. In order to understand this idea of the atoms being electrically charged, and we can go over this in class, we have to understand that in normal conditions, an atom is neutral. It has an atom is made up of particles that are positively charged, particles that are negatively charged, and particles that are neutral. Okay, the center of the atom, or the nucleus of the atom, is where the protons and the neutrons are. The protons are positively charged, the neutrons are neutral, and then around the nucleus of the atom are the electrons, and the electrons are negatively charged. And under normal circumstances or conditions, if I could simplify it here, basically the number of protons in an atom equals the number of electrons, which means the number of positively charged particles equals the number of negatively charged particles, which means the atom has a neutral charge. 3 positive charged particles cancel out 3 negative charged particles. Okay, but energy can change this, and you can change electrons in an atom. You can add electrons or take electrons away. The way we change the charge of an atom is by adding or taking away electrons, which means we change the charge by adding or taking away negative charge. If you add electrons, you're adding negative charge. That atom now has a negative charge, and it's called an anion. An ion is any atom with a charge. An atom with a negative charge is an anion, A-N-I-O-N. If you take electrons away, you're taking negative charge away, which now means that the overall charge of the atom is positive, and we call that a cation, C-A-T-I-O-N. Pretty easy to remember, guys. A in front of anything means take it away. So anion, right, negative. Cation, T is like a plus sign, positively charged. Now, what does all this have to say? Well, when we charge, electrically charge, or use heat to add energy to an atom, it can cause the electrons to move places, stay within the atom, but move places. Those electrons want to be in their natural space or natural state. And so once the energy is removed, they will drop back down to where they would normally be. And when they drop back down, they give off energy. And that energy can actually be seen by us as different wavelengths, and those wavelengths give us color. And this is happening. You're pounding these nitrogen and these oxygen atoms with all this energy, X-rays and gamma rays. They become electrically charged. The electrons do their thing. And this is all happening up in the thermosphere. And then they give off these wavelengths of energy that are observed by us as different colored lights. Okay, so as they become electrically charged, they're ions. In the lower part of the thermosphere then is called the ionosphere. And all kinds of things happen. Those ions radiate energy as lights. The lights glow. We see them, north and south poles. And this is how the northern lights for the aurora borealis are actually created. We use the same principle in chemistry. Time and time again, I have done what we call flame tests. And you can take different salts. Right, we all know sodium chloride is a salt. Well, magnesium chloride is a salt, and calcium chloride is a salt. These metallic salts, and you can take these salts and put them on a wire loop and put them in a flame, and get these bright, almost like firework type colors, bright greens and purples and oranges, and they have to do with the number of electrons that are present that are jumping from energy to energy. And you can actually identify what metallic salt you're dealing with based on the color. The magnesium chloride salt is not going to give off the same color as the calcium chloride, so on and so forth. But in terms of the atmosphere, the same thing is happening with the nitrogen and oxygen atoms. They're being turned into ions. They're giving off energy in visible wavelengths, spectacular colors. We see this as the northern lights or the aurora borealis. Now, how does energy transfer in the atmosphere? We've talked a little bit about energy, and this is going to have a connection to weather and some other points. There's three things I want us to see: radiation, conduction, and convection. Radiation is the energy that is transferred as electromagnetic waves such as visible light and infrared waves. Let's just define these guys. Conduction is the transfer of energy as heat through material. Convection is the movement of matter due to differences in density that are caused by temperature variations and can result in the transfer of energy as heat. So if we look at each one of these, see what we're talking about. Radiation is what we were just talking about. Gamma rays, X-rays. They bombard these atoms, okay? And it's actually energy moving from one place to another. But conduction is different. When you have one piece of matter that is hot, another piece of matter next to it, the heat or the energy travels through. Conduction is when I take my frying pan and I put it on top of my electric element, on top of my electric stove. I'm running electricity through that metal on the stove, and that electricity is causing the particles of that metal coil to vibrate faster and faster and faster, which we see and feel as heat. And because that is the frying pan's on top of that, okay, that vibration starts to transfer to the particles in the frying pan, and now the frying pan is hot, okay? And then convection has to do with the movement of matter, because heat and cold is connected to density. So if I have a warm air mass, particles are moving faster and faster, that air mass becomes less dense and it goes higher. And it brings that heat energy with it and then can transfer that heat energy. It displaces a colder air mass, which then sinks down to the earth. If any of you have ever ridden in a hot air balloon, you understand this concept. A hot air balloon does not float because of helium or anything like that. Basically, you have your burner, you have your propane, and you are superheating the air inside of the envelope of that balloon. Eventually, that balloon, the air within that balloon becomes much less dense than the air around it. The balloon starts to rise, and then you start to rise with it. Okay, that's a great example of convection. This diagram, which is in your book, shows how all this can happen. Radiation moves energy through space in waves to heat the surface of the Earth. Near the Earth's surface, air is heated by conduction, and then convection currents are caused by the unequal heating of the atmosphere. And we see how all that plays out. Warming of the atmosphere. Solar energy reaches the Earth. Electromagnetic radiation, we've talked about this. This is visible light. This is infrared. This is UV. All of that in different amounts getting to the Earth, increasing the energy. Half of the solar energy that enters the atmosphere passes through it and reaches the Earth's surface, while the rest is absorbed, reflected. This clouds, gases, dust. That's very important, okay? The fact that we have an atmosphere that's in place, the fact that we have a system that's in place that allows half of the solar energy to get through, imagine what life would be like on the surface of the Earth if more than half got through. Imagine what life would be like on the surface of the Earth if less than half got through. There's a perfect narrow window there, and for life to be sustainable on the planet, it needs to be at or near that number. Now, the Earth does not continue to get warmer, even though we get that day after day. We have these oceans, which really we can view as like the big thermostat of the planet, because water functions differently than land. It takes longer for water to heat up, takes longer for water to cool down. So you have the oceans, then you have the land, and a lot of that energy is radiated back into the atmosphere every evening or overnight. We know this in terms of how dark-colored objects tend to absorb solar radiation. In the northeast, where I'm from, very often roofs are made out of dark-colored materials so that they will absorb more solar radiation in the winter to help snow and ice melt. Okay, lighter colored objects reflect it, and so we can see how that plays out and how this plays out on the planet. Temperatures in cities tend to be higher. Large cities create their own weather because large cities create what we call heat islands. If it's July and you go into New York City, it might be 98 degrees. If you drive an hour and a half north into the country, it might be 85 degrees. Literally, there's that much. It can be a 15 to 20 degree difference. And that heat makes a lot of moist air go up in the air and creates a lot of precipitation. So cities actually make their own weather because of this phenomenon. Now, this understanding of convection helps us understand wind currents and other movements within the atmosphere. Current of air, what happens, it's warmed by the Earth's surface, it rises, it begins to cool, and eventually as it's cooling, it becomes more dense than the air around it, and it sinks again. And as it comes closer to the Earth, it is warmed, and as it's warmed, it rises again because it comes less dense. And this creates these circular convection currents that create wind. One of the concepts I want you guys to start getting out of here is that at the end of the day, the sun ends up being the engine that drives everything on the planet. Wind currents, weather, ocean currents, the food chain. In a very real sense, everything we talk about in this chapter can be traced back to the sun. Wind currents exist because of the sun and the energy that it puts into the planet. Continual process of warm air rising and cool air sinking, moving in a circular motion, is what we call convection currents. This brings us to the greenhouse effect, and I want you guys first off to understand something. When I was in upper elementary school, middle school, and high school, the greenhouse effect was something that was talked about quite a bit, and unfortunately it was talked about in such a way that we automatically assumed the term greenhouse effect had a negative connotation. The greenhouse effect in and of itself is not a bad thing. It is a natural phenomenon. Okay? It is a designed operational tool of the atmosphere. The warming of the surface, lower atmosphere of the Earth occurs when carbon dioxide, water vapor, other gases in the air absorb and re-radiate infrared radiation. Helps the planet maintain the temperature to sustain life. The atmosphere functions like a greenhouse. If there was no greenhouse effect, the Earth would be too cold for life to exist. Okay, so the greenhouse is, regardless of what is said about it, and we're gonna watch a movie about global warming that has scientists presenting different models than maybe what you've normally been presented with. Regardless of all that, it is a needful operational paradigm in order for life to be sustainable on the planet. Now, the textbook here uses a car, and a car is fine. I don't know why they use a car as an example. It's called the greenhouse effect. We could talk about a greenhouse, show a picture of a greenhouse, right? A greenhouse is a building. It's made out of glass or made out of plastic. It allows the energy from the sun to pass in. When that energy gets in and bounces, only a small percentage of it can pass back out. Much of it is trapped by the glass or by the plastic, and the interior ends up warming up like the inside of your car, okay? But it's called the greenhouse effect, not the interior of your car effect. So let's think about this in terms of a greenhouse. That energy comes in, much of it gets trapped, increasing the temperature therein. The gases in the atmosphere that trap and radiate the heat, the gases that in our example would be the glass or the plastic that make up the walls and the roof of the greenhouse, those are called greenhouse gases. The most abundant greenhouse gases are water vapor, carbon dioxide, methane, and nitrous oxide. None of those exist in high concentrations. Remember, guys, all of those fall into that 1% piece of the pie. You have more than likely heard over and over and over again that carbon dioxide is the most important greenhouse gas. And I want you to understand that there are atmospheric scientists who will tell you the exact opposite. What we know now is that water vapor is the most important greenhouse gas. If that is true, then everything we've heard about carbon dioxide, everything we've heard about carbon footprint, everything that we've heard about reducing our carbon emissions to stop global warming is based on a model that is incorrect. So keep that in mind. Carbon dioxide and methane in the atmosphere vary considerably as a result of natural industrial processes. We knew this. I already mentioned the fact of volcanic activity. But let's be honest, the amount of water vapor in the atmosphere varies considerably too. Okay? So, again, lots of different models. As scientists, we need to be open to the explanations that are out there.